Welcome to this lecture on linear operators. The first part will be dedicated to the basic definitions and properties of linear operators. Then we go into some of the fundamental theorems which are at the core of function analysis, and we'll finish with some special operators like invertible operators, for example. Okay. Let U and V be two norm spaces. So these are two vector spaces, normal vector spaces, and a priori these two normal vector spaces are different. And if they are different, it means at least that the norms are not identical, okay? And in this case, we'll call the norm sub U, the norm sub V are the norms considered on U and V. Okay? So we take a map T that goes from U into V, and we say because we have the linear structure that number one, T is additive if and only if T of U1 plus U2 is equal to T of U1 plus T of U2 for any U1 and U2 in U. We will say that T is homogeneous if and only if for every lambda in R, for every U in U, we have T of alpha U equals, I'm sorry, not alpha, lambda equal lambda T of U. And finally, we will say T is linear if and only if T is additive and homogeneous. T is additive and homogeneous. Okay, the set of all the linear operators will be denoted by L of UV. So this is the set of all T's, T which goes from U into V, which is linear. Okay, this space here is not equal to 0 because we can take the 0 map is linear. In other words, the constant map that gives for every vector U in U 0 in V. So belongs to L of UV. Okay, so it's linear and therefore it belongs to LUV, so LUV is not empty. Okay, we always have at least that linear map. And it's easy to see that LUV is a linear vector. LUV is a vector space. Okay, we can always define the sum of two maps, which is still linear, and we can multiply a map by a constant and get a linear map. Okay, so next we discuss the norm, the topological properties that we get from the norm in this setting. Okay, at least on LUV. Okay, so first let us discuss the continuity Okay, and we'll say that T, let T belongs to LUV. So it's a linear operator from U into V. Okay, let U0 belongs to U. T is continuous at U0 if and only if limit T of U when U goes to U0 is equal to T of U0, which is the same as for every epsilon there exists delta positive such that the norm of U minus U0 in U less than delta imply that the norm of TU minus T of U0 in V less than epsilon. Since T is linear, T of U minus T of U0 is just T of U minus U0, which suggests that since the vector U minus U0 is small, that maybe what we have is a continuity at 0, and that is true. So, okay, if T is linear and continuous at U0 at some point, okay, in U, then T is continuous at 0. Okay? Indeed, let epsilon be positive, there exists delta such that U minus U0 less than delta imply T of U0 less than epsilon. Okay? So let W be in the open ball 0, 0, delta, and this of course in U. Then the norm of W in U, I forgot to mention this is U and this is V, and the same goes for the one before. Right. So less than delta, which implies W plus U0 norm is less than minus, which implies that the norm of W plus U0 minus U0 less than delta, which implies from the continuity that the norm of T of W plus U0 minus T of U0 in V is less than epsilon, or the norm of TW, using the linearity, of course, of less than epsilon. So you see, for every epsilon, we found delta. For every epsilon, okay, we found delta, such that for every W that satisfies this, we have this. Therefore, T is continuous at 0. So T is continuous at 0. So assume T is continuous at 0. So for every epsilon, there exists delta positive such that Okay, for every u in u, norm of u in u less than delta, imply the norm of tu in v is less than epsilon. Okay. Now, let u0 belongs to u be any vector. Be any vector. Okay? Then u0 plus the ball in u using the linearity of the space is just the open ball in u of u0 delta. Okay? So we have for any w in the open ball u0 delta, we have the norm of w minus u0 in u less than delta. Okay? So using the continuity of t at 0 that we said before, then we get that t of w minus u0 in v less than epsilon, which implies, obviously using the linearity, which implies that the norm of tw minus t of u0 in v less than epsilon. So that what we proved is that if t is continuous at 0, is in fact continuous anywhere, at any point. In other words, we have the following beautiful result, theorem. Let u, v be two normed vector spaces. Let t belongs to L, U, V, and the following are equivalent. Number 1, t is continuous at 0. Number 2, t is continuous on u. So we have the continuity at one point gives us the continuity on the entire space. So this is one of the beautiful properties of linear operators. Next, from now on, either we say it's continuous at 0 or continuous everywhere. We know it's going to be the same. So assume t belongs to L of uv and continuous at 0. Okay? Then for every epsilon, there exists delta such that the norm of u in u less than delta implies the norm of t of u in v less than epsilon. Okay? So now let u be in a vector in u, okay, such that, okay, let u be in u. Let R be bigger than the norm of u. Okay, it's enough to take R equal 1 plus norm of u. Then if we take u, let's say the vector, the norm of the vector delta of 2r times u in u is equal delta of 2r. Keep in mind that r is bigger, so it's not going to be equal to 0. Norm of u, and this is of course less than delta, okay, because in fact it's less than delta over 2, which is for theory less than delta. So t of delta over 2r u is less than epsilon, and this gives us that norm of t. By using the linearity, we can take delta over 2r out of u, delta over 2r, v less than epsilon, or norm of tu over v less than 2 epsilon r over delta. Okay, so since this is true for any r bigger than the norm of u, okay, true for any r greater than the norm of u, we get by letting r go to norm of u, we get that the norm of tu, which is independent in FEM over all these ones, is less or equal than 2 epsilon over delta norm of u. Another way to see this inequality is to say, okay, if u is equal to 0, this inequality is trivial. So you start with u not equal to 0. And in this case, what you do here, you take r, this r, you take it equal to the norm of u. Okay? So this way, when we divide, we're going to find the norm here. When we divide here, we're going to find norm of u over r, which is norm of u over norm of u, and that's 1, that's delta over 2 less than delta. So we have a choice. Either we do it in 2 times, or we do it like this. Okay? Good. So what happened is that conclusion here is that if t is continuous at 0, then there exists a constant c such that the norm of tu in v is less or equal than c norm of u in u for any u, for any u in u. Okay? Conversely, assume that there exists c greater than 0 such that for every u in u, we have the norm of tu in u less than in v times norm of u in u. Okay? So in this case, by linearity, we get for every u v in u, we get the norm of tu minus tv, which is the norm of u minus v by linearity of u, less than the norm of u minus v in u, which implies that t is Lipschitzian. Mapping, and we know that so t is uniformly continuous, not only is continuous but uniformly continuous on u. So here in particular it is continuous 0. So here we have a beautiful theorem. Let t be a linear product from u to v. The following are equivalent. Number 1, t is continuous, whether at 0 or everywhere, doesn't matter. 2, there exists a constant c such that for every u in U, we have the norm of TU in V less than C norm of U. Okay? So such property here, what's amazing is, so here we say that T, if T is a linear operator which satisfies 2, is said to be bounded. So bounded operators, the family of bounded operators would be called the class of T in linear operator such that T is bounded. Okay? So this is the family of all linear operators which are continuous. Okay? Before we proceed more on bounded linear operators, we don't want anyone to believe that the space, because here we do have B of UV is a subspace of L of UV, and it's a linear space. It's a linear subspace of LUV. I don't want anyone to believe that they are equal. They may be different. Let's just give an example of this. So, which means that there are unbounded operators. So, example, let U be of 0, 1. So these are continuous functions defined as 0, 1, which are differentiable and they have continuous derivative, and V is equal to continuous functions of 0, 1. And in fact, U is a subspace of V. Okay, it's a linear subspace. They are normed. We are going to take for both spaces. We will take the same norm. We will take the sup norm. Okay, so for any f in U or V, we have the norm, the same norm, the norm of f to be the sup of absolute value of f of x, x between 0 and 1. Okay? So consider now the operator D from U into V, which gives us the derivative. Okay? Then if we take D of E minus nx, we're going to find minus n E minus nx. Okay? So the norm of E minus nx, this is equal to 1, while the norm of D of E minus nx is equal to n, is unbounded. So operators can be unbounded. So we don't want, so D here, so belongs to LUV, so D from your basic calculus, okay, is a linear operator, so it belongs to LUV, but D does not belong to the bounded family of bounded operators, linear operators between U and V. Okay? So they can be different. Let T be a linear operator between two normal vector spaces. We can define the null space, define the kernel of T, or the null space of T to be n for null space and ker of T for the kernel to be the set of U in the U such that T's of U is equal to 0 vector in V. Okay, this is a linear subspace associated to T, and n of t can be seen as the inverse image of 0. So in general, this subspace may not be closed, but if t is continuous, okay, then the kernel or the null space is a closed subspace in V, in U. Okay? That's not the case for the range. So this is the kernel. But if you take the range, so the range of T is defined as, these are classical subspaces associated to any linear operator, R of T to be T of U, which is a subspace of V. So this is TU, U belongs to U. So you see this is a subspace of V, okay? The kernel or the null space is a subspace of U, while the range is a subspace of the target's vector space V. So since this is the image for a continuous map, we don't know if it's closed or not. So this is not clear. If T is bounded, okay, then we can't conclude that R of T is closed or open, as a matter of fact, because the entire space U is closed and open, so we don't know. Okay. Let us go back to show that B of UV is in fact note that if T belongs to B of UV, then the sup of the norm of TU when the norm of U is less than 1, this is finite. Okay? This is V, the norm in U. So you see, this quantity here is the smallest constant C in the definition of boundedness. Okay? So we know that this quantity here will be finite because T is bounded operator. Okay? Set the norm of T to be the sup of TU when the norm of U is less or equal than 1. I said norm of T because in fact this function here defined on B of UV into the set of positive number is a norm. So this of course is obtained from the properties of the norm in V, the definition of the sum of two operators, etc., etc. So it's a very simple, fairly simple exercise to show that this is a norm. Okay? So we have now a norm. Note also that the norm of T can be also equal to the sup of the norm of TU, okay, where the norm of U is equal to 1 in U. Okay, so it's the same quantity. Okay, so we have a norm now. This implies conclusion. The space of bounded linear operator is a normed vector space, and throughout we'll always consider the same norm, this norm here. Okay. on the bounded linear operators. Okay. So note that, as we said earlier, bounded linear operators are in fact uniformly continuous, and therefore, as we did in the metric spaces, we have this kind of extension to the completion. Okay. So here, let me explain this. Call it extension of bounded linear operators. Let T belongs to BUV. So V and U and V are two normal linear spaces. T is a bounded linear operator. Okay. Let U bar be the completion of U. Completion of U. It's easy to see that U bar is a Banach space. Inherit all the properties because of the density of U in U bar. Is a Banach space. And for any U bar in capital U bar, there exists a sequence UN in U such that the limit of UN is equal to U when n goes to infinity. So in this case, we conclude that T, okay, so here, assume first, just let's show something interesting. Assume that UN and Vn are in U such that limit of Un minus Vn is equal to 0. Assume that we have two sequences in U such that their limit is equal to 0. Then it's easy, from the continuity, it is easy to see that limit of Tun minus Tvn when n goes to infinity is also equal to 0 in V. Okay, because T is bounded, therefore it's continuous, then we get this property. So now let U belongs to U bar. Okay, we know that there exists Un in U such that Un limit of Un when n goes to infinity equals to U bar. Okay, so since Un is a convergent sequence, it's Cauchy. So Un is Cauchy. Okay, and since it is uniformly continuous, then Tun is Cauchy in V. So in this case, if we assume that V is a Banach space, so assume V is a Banach space, complete, then limit of Tun when n goes to infinity exists in V. Okay? So, but what's interesting from what we said earlier is that if we have two sequences which converge to U bar, Un and Vn, from here, okay, then we are going to have the limit of un minus vn is equal to 0, and then the limit of tun minus tvn is equal to 0, but we just said that the limit of tun exists and the limit of tvn exists. So in this case, they have the same limit. So this limit, in fact, is independent of the sequence un. Okay? So let us write t bar of u bar equal limits of tun when n goes to infinity. Then this defines a map t bar from u bar into v. Okay? It's very easy to see that if u belongs to u, then t bar of u is equal to t of u, because we can take the trivial sequence with the constant sequence equal un equals u for every n, and this will give us that the limit of tun is equal to t of u, and therefore t bar of u. So t bar, in fact, is an extension, and it's also very easy to see from the properties of the norm, okay, and the continuity of the norm, that for every u bar in u bar, we have the norm of t bar u bar in v is less than the norm of t norm of u bar in u bar. Okay? In other words, that t bar inherits most of the properties of t. Number one, it belongs to L of u bar v. And number two, t bar is bounded. Okay, and the norm of t bar is less or equal than the norm of t. In fact, it's not less or equal, it's equal because it's an extension of t. In fact, we have the norm of t bar equals the norm of t. This extension, in fact, what it does, that it suggests the following. This extension suggests that when dealing with bounded operators, then we can, without loss of any generality, without loss of any generality, we can assume U is Banach whenever V is a Banach space. Okay? Next, let V be a Banach space. And U be a normed vector space. Let Tn belongs to B of UV. Okay. Such that the sequence Tn is Cauchy. In other words, for every epsilon, there exists n0, such that for every n and m greater than n0, we have the norm of Tn minus the norm of Tm less than epsilon. Okay? So let U belongs to U. Then it is easy to see that Tn of u is Cauchy in V. Since V is a Banach space, then limit of Tn of u when n goes to infinity exists in V for any u in u. Set T of u equal limit of Tn of u when n goes to infinity. So T is well defined from u into V is well defined. Okay? Okay. Using the properties of the Tn's, since the Tn's are all linear, since the sequence Tn is in L of uv, we get, and of course we are using the continuities of the additional multiplication by scalar, we get T belongs to L u uv. Okay? Moreover, since the sequence Tn is Cauchy, then the sequence norm of Tn is bounded. Okay? So from there we can show that for any u in u, we can show that the norm of Tu in V, which is limit, again using the properties of the norm and the continuity of the norm of Tn of u in V, which is less than the sup of the norm of the Tn's norm of u in u, and this is n greater than 1 because they are bounded, so the sup is very well defined. So this tells us, in fact, that T, so T is bounded, and the norm of T is less or equal than the sup when n greater than 1 of the norm of the Tn's. Okay? So, what's the conclusion of this? The conclusion is that if u is normed and V is a Banach space, then B bounded operators from U to V is a Banach space. This is a beautiful result. Note that we have a special case of the finite dimensional case. I say if we assume that V is a finite dimensional space, then, okay, in this case, L u v is exactly B u v. In other words, any linear operator is bounded. Okay, and it's very easy to see this. We know that the bounded linear operators are already in LUV, so let T belongs to LUV. Okay, and since V is a finite dimensional space, we know it's going to be the span of a basis E1, En, n greater than, sorry, for n fixed, where n is the dimension of V. Okay? Then I made a little mistake here. I don't mean V, I meant U. Okay? Okay? So for any U in U, we know that U is going to be equal to alpha 1 E1 plus alpha n En. Okay? So the norm, first Tu is going to be alpha 1 T of E1 plus alpha n T of En. Okay? And this will imply that the norm of Tu is less or equal than the max of the norms of the TEIs in V, sigma of absolute value of alpha i's from 1 to n. Okay? But we are in a finite dimensional space, and we know that all the norms are equivalent. We have seen this in the in the lecture on normed vector spaces. So in this case, we know that there exists a constant alpha positive such that sigma of alpha I from 1 to n, which defines a new norm, the L1 norm, a new norm on U. So this will be less than alpha norm of U in U. Okay, all the norms are equivalent. So this sigma of absolute value of alpha I will define a norm on U. Okay, so that's why we have this inequality. And in this case, we get so the norm of Tu, okay, in V is less or equal than alpha, the max of the norm of TEIs, I between 1 and n, and norm of U in U. In other words, T is bounded. Okay? So T is bounded operator. Next, we discussed another operation on the operators, which is the composition. Okay, the composition here of operators. And to make it easy on us, let us take the case when U, okay, U is equal to V. So in this case, L of U, U will write L of U, and B of U, U is equal to B of U. Okay? So it's very easy to see that if A and B are in L, U, two linear operators, then A composed with B is also a linear operator. Okay? Recall that A composed with B of U is equal to A of B of U. Okay? For any U in U. Okay. Now, okay, let A and B bounded operators, B of U. Let U be any vector in U, then the norm of A composed with B of U in U. So we're not going to write in U because it's the same space anyway, so we have only one norm. and this is equal to the norm of A of B of U, and this will imply this is less than the norm of A norm of B of U, and this is less than the norm of A norm of B norm of U. Of course, so this tells us what? That if A and B are bounded, then A composed with B is also bounded, and the norm of A composed with B is less than the norm of A times the norm of B. We can easily extend this business to any Banach spaces U and V. I'm just trying to show how the composition also stays the same. Otherwise, we can take A that goes from U to V, and B that goes from B that goes from U to V, and A that goes from V to another space W, three normative vector spaces, and then we take the composition, and then we'll take the LUV, LVW, LUW for the composition, and we'll have the same result, exactly the same. I wanted just to illustrate how the composition, in fact, preserve this kind of now what I wanted to show is that the next one is that if beautiful, assume that AN and BN are in B of U, so these are bounded linear operators, such that limit of the AN is equal to A and limit of the BNs is equal to B when n goes to infinity. Okay, so in this case, using this inequality that A and B and minus A composed with B equal the norm of A n composed B n minus A n composed with B plus A n composed with B minus A composed with B norm. And this is less than the norm of A n composed with B n minus A n composed with B plus the norm of A n composed with B minus A composed with B norm. Okay, this is the triangle inequality on the norms of the operators. And this, of course, since the ANs converges and the BNs converges in norm, they are bounded. They have bounded norms. So in particular, this is less. First, this is equal. Sorry. This is equal norm of AN composed BN minus B plus norm of AN minus A composed B, which is less or than the norm of AN, norm of BN minus B, plus norm of AN minus A, norm of B. Okay? So, since the BNs converge to B and ANs converge to A, this will go to 0, this will go to 0, but the ANs is bounded, and this one is just a number here. So what we have is that the limit, this will imply that the limit of AN composed with BN is equal to A composed with B when n goes to infinity. So in other words, we have a new operation on the bounded linear operators, which also is continuous. So this composition here for every pairs AB gives A composed B is continuous. And when this happens, so we have now what? We have B of U we have the addition, we have the multiplication, and we have the composition, and this behaves like what we call a Banach algebra. Okay, a Banach algebra, assuming, of course, that U is a Banach, so this gets one more operation, natural operation. The linear operator is defined from U into U, gives us a structure, a richer structure with one more operation, and this gives us what we call a Banach algebra structure. Okay. Thank you very much. And next we'll discuss some of the fundamental theorems related to boundary linear operators and linear operators in general. Okay.